Well, good day, students. Welcome to the last week of lessons. I have 6 more to record for the rest of the year, and then that'll be it. So, as far as new lessons, after that, we'll be working to help those of you who are behind catch up, and to help those of you who are trying to earn exemption get that earned. Anyway, that's what'll happen. But these are the last lessons we have to do. And we're going to talk about vectors. Now, last time we met, we talked about them component wise, the XY components of a vector. And now we're going to talk about magnitude and direction of vectors. Now, the magnitude is just how long, it's the length of a vector or distance, etc., etc. And the direction will be an angle typically measured from the x-axis counterclockwise that the direction is moving. So the angle will define the direction. So if you have the initial and the terminal points of a vector, then you can find the magnitude. And this will look very familiar. We've been doing this kind of thing all year long. But if I had an initial point and I had a terminal point, so I'll just label them I and T, and I we're going to call x1, y1, and T we'll call x2, y2. All right. And that's our vector right there, that directed line segment. Then we can find the magnitude. It just refers to how long the vector is. And of course, you can always draw a right triangle in this situation. And now this looks just like the distance formula. So we're going to call this vector v, okay? And so we're going to say vector v has a magnitude, and this is the notation. Magnitude of vector v is equal to basically the distance formula. So x2 minus x1 squared plus y2 minus y1 squared. And if you look at that, if we found the length of a radius, we use the Pythagorean theorem. The distance formula is just the Pythagorean theorem in disguise, etc. So there we go. Now, if your vector happens to be a position vector in component form, so this is where you would write the vector as x, y, and this would be your terminal point right there. The initial point is the origin. So if you have a position vector like this, then the magnitude of the position vector, again, this would be the length of x, this would be the length of y, and by the Pythagorean theorem, it would just be x squared plus y squared. And if you want, you can think of that as x minus 0 squared and y minus 0 squared, because the initial point is 0, 0. So if you have a component form vector, this would be the magnitude. But this is the overall formula that works in all cases, whether it's in component form or it's given as initial and terminal point. So the first problems you have to do are find the magnitude of a vector. So if we have a vector, let's say we have a vector here, and it's 5, 13, and it's a position vector. All right, and we'll call it vector v. And we want to, so the component form is 513. All right. And we want to find the magnitude of that. Then we can find the magnitude of vector v, which could be written as the magnitude of the vector written in component form. You could write it like that. And that's just going to equal the square root of x squared plus y squared, which is 5 squared plus 13 squared, which is the square root of 25 plus 169, or the square root of 194. All right, and then you can simplify this. If it simplifies, it doesn't, or you could leave it like that. Okay, so that's really the first part of the problem. Now, we should probably talk about, there's one more thing that we need to discuss, and we can do this in 3 dimensions. So 3D. So you could say the magnitude of a vector in 3D, it would be the extended Pythagorean theorem, so x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. And that's if you had initial and terminal points. Initial and terminal points. That would be the magnitude. If it was a position vector, which means the initial point is 0, 0, 0, and you are given it in component form, just x, y, z, and you can tell when the notation uses these chevrons. All right. Anyway, if it's given that way, then the magnitude of the vector will equal just the square root of x squared plus y squared plus z squared. So doing this in 3 dimensions is just an extension of the 2-dimension situation. Okay, let's move on. So we are learning lots of ways to write vectors. You could write vectors given an initial point and a terminal point. So these would be points, and so it'd be like x, y, z is the initial point, and the terminal point is a, b, c. Or that would be 3 dimensions. In 2 dimensions, it'd be like x, y, and a, b. And so you'd say, I have a vector from blank to blank, like that. Okay? Initial and terminal points. You can also write a vector as a position vector. And this is where we use the vector notation. And then position vectors always have initial point at origin. Okay? And now we're going to start writing vectors in terms of magnitude and direction. And so we could take a vector and we could write it like this: the magnitude of a vector and its direction given by an angle. And so that's another way we write vectors. Now, with vectors, we tend to put the measurement in degrees. Okay? All right? And then the component form of the vector can be calculated just by using trigonometry at this point. All right? So, let's go ahead and play some games and write this out. Let's go back and forth. All right? So first of all, we're given a vector. Let's call it vector W. And we're going to call the vector 3, negative 2. Okay? That's our vector. If you want to look at it geometrically, it looks like this. Okay? All right, that's what it would look like, 3, -2. Okay, so what we'd like to do is we would like to write it in magnitude and direction form. And so the magnitude of vector W, which is the magnitude of 3, 2, now 3, -2. Now notice this is a vector in position form or component form. All right, component, position, kind of mean the same thing. So component form, all right? So we know the x, y, we know 0, 0 is the other point, so the magnitude is just the square root of 3 squared plus -2 squared, all right? Which will be the square root of 9 plus 4, or the square root of 13. So that's the magnitude. Now we want to find the angle. And the angle is always going to be the angle counterclockwise going around, okay? And we may need to use a reference angle. Remember, good old reference angles to help us find that. And so we're going to do that. So if I draw this just a little bigger, then this is 3, this is the -2, and we can find the angle by what? Theta, the inverse tangent of theta equals the inverse tangent of opposite over adjacent, -2 over 3. And so if I can calculate this in degrees, which is fairly simple to do on a calculator, so really quickly we'll go ahead and do that. Let's go to the browser, go to the Desmos Scientific Calculator. Notice my mode here is degree mode, all right? And so I want the inverse tangent of, I go back to the main menu, -2 divided by 3, and press equal. And so that is -33.7 degrees, all right? So there's my calculation right there. So this is equal to -33.7 degrees. Okay, now that's down, and the angle we want the angle counterclockwise, so we basically subtract that from 360, all right? And so we could take 360 minus 33.7, which will give us 326.3 degrees, all right? And so that's our angle, theta is equal to that, and so we can write W in component form is 3, -2, which is now equal to the magnitude square root of 13, comma 326.3 degrees. Okay? So that's how we find the direction. Okay? And so now here's my vector written in magnitude and direction form. All right? So let's go the other way. All right? So the other way is, suppose we have a vector already in magnitude and direction form. Can we find the component form? All right? And that's what we want to be able to do. And so suppose somebody tells me now vector W is equal to, so let's give it a magnitude, let's call it 5, and let's give it a direction, and we'll give it a special angle. So let's go 210 degrees, all right? And so if you look at this is kind of a polar form graphing. The magnitude is like the radius, and the 210 is like the theta. And so if you were to look at this, you would go 210 degrees, which would be right there. And then you would go out 5, and that's where the vector is. So now we want to write this in component form. So I want you to think about this trigonometrically at first, okay? What we have here is we know the radius, and we know that the reference angle here is 30 degrees, okay? Why? Because 210 minus 180 is 30. So that's the angle right in there, even though all the way over it's 210. So that's 30 degrees. And so since I have that angle and this side, I can find this side and this side, which are the component forms, the x and the y, that I need. And basically, by trig, I can say that the sine of 30 degrees is equal to the opposite, y over 5, okay? And I can say the cosine of 30 degrees is equal to the x over 5. And now I just solve those. And so I get here, I would get 5 sine of 30 degrees equals y. And here I would get 5 cosine of 30 degrees is equal to x. So I can get y equals and x equals. Now, the sine of 30 degrees, that's a special angle, so I can just do that one in my head. That is 1/2. So y is 5/2, 1/2 times 5. If it was like 35 degrees, I would just use a calculator, all right? Cosine of 30 degrees is square root of 3 over 2, so this is 5 square root of 3 over 2, all right? And so therefore, W, which was equal to magnitude 5, 210 degrees, is now equal to x, 5 square root of 3 over 2, and 5/2. So this is the component form, which would basically be, you would go, let me look at this. Since it's 210, okay, the y, we got to talk about the y for a minute. So this gives me the correct size, but it doesn't give me the correct direction. Notice how the y is negative. So I would put a negative here. Okay? Now, I did this more like a trig problem. So anyway, this is the correct answer. 5 square root of 3 out, and then negative 5/2 down will get us in the right spot. So this is the correct component form. So let's talk about this. I just did it in a trig way. And what I want to do is I want to do it in more of a how they give it to us. And so what they do, what we need to look at is we need to look at this right here and this right here. And so question, why did this not give me the correct negative sign? Okay, well, because I used 30 degrees, which is actually a first quadrant angle, all right? And I was looking at this as just a triangle. But in vectors, we don't have to look at it as just a triangle. We can actually look at that whole angle all the way around. So instead of putting the sine of 30 degrees, I could essentially notice the 5 is actually the magnitude and the 30 is the reference angle for the 210. So what we could have written is we could have said the magnitude of W times sine of the angle is equal to Y. And the magnitude of W times the cosine of the angle is equal to X. Now, I just want you to notice that this is actually the radius of a circle times sine theta. These are actually the conversions that we used for polar coordinates. Okay? They're just written out in vector language. So I could have taken the magnitude of W times the sine of 210 degrees to get the correct sine value for the vector, because I don't have to pay attention to triangles here. And I would have gotten negative 5/2 for that. And then I could have taken 5 times the cosine of 210. And I would have gotten the correct sine value for that as well, which is negative 5 square root of 3 over 2. So the reason I did it this way is I just wanted to show you, you could use trig to figure it out. But when you're doing vectors, we got to watch out for those signs. And so we want to actually use the angle of the vector. And that would have given us a negative in each case. So the component form is x negative 5 square root of 3 over 2 and the y negative 5/2. Okay? And here's the formulas, which are very similar to our polar coordinates, or very similar to how we might calculate values based on what quadrants they are in. Okay? And so even though I get a value, then I got to think about the sign. That's what we did in trig. But now in the vectors, we can just do it by the formula, and it pops right out. Okay? All right, let's move on. Okay, so we're going to look at a practical application, and we want to look at words and notation here for real world distance and direction. Okay? So if somebody writes 40 degrees north of east, okay, what they mean is if you have north, south, east, and west, okay, then when they say go 40 degrees north of east, that means you want to go 40 degrees north in the north direction from east. So this is the words, all right? So now let me write this same vector in notation. In notation, we would say it's 50 degrees. We would say north 50 degrees in the east direction. All right? Which means we're going north and then we go 50 degrees towards the east direction. Now notice how these are complementary in the way they're written. Okay? So north 50 degrees in the east direction. Okay? Got it? That's how you take compass headings. Now, by the way, surveyors have to know this in order to be able to survey land, because property lines are recorded in this way. If you ever get to see the deed or the home loan paperwork, you should ask your parents, you should look for the map, what will be called a plot map of the your property that your home is on. And if you look at the boundaries, you will see that the boundaries are often recorded in one of these two ways. Okay? And so surveyors have to know that, and all property, though these things are pretty big deal. And that's why you'll see the metal stakes either painted orange or at my property, they actually have a yellow tab on top that says this is a corner of your property. And so it's a big metal bar pounded in the ground. All right? So that's how you can describe a vector. Okay? All right? You can say 40 degrees north of east, or you can say north 50 degrees east, or you could say a bearing of blank. So in this case, it would be a bearing of 40 degrees. And so you just measure from the horizontal to whatever it is. Now, if you're over here, your bearing's going to be bigger than 180 degrees. Okay? But those are the three ways you do it. And you need to definitely understand that. Okay? Now, well, another thing you need to know about real world problems is rate times time equals distance. Or in vector language, rate times time equals magnitude. Okay? How long it is, how far you go. So, if you drive 75 miles per hour, all right, and you do, or 70 miles per hour, and you do that for 2 hours, all right, then the magnitude is going to be 140 miles. Okay? How far did you go? All right? So let's move forward and look at some problems. So let's say you are driving on a road, okay? All right. And you drive on a road for 3 hours at 60 miles per hour, okay? And that road is out like this, okay? And so this is like 20 degrees, okay? 20 degrees. So describe the vector that goes with this situation. So one way to do it is we want to take the magnitude of the vector. So the magnitude in this case is 3 times 60, or 180 miles, okay? And then the direction of the vector, there are 3 ways we can do the direction. Since this is 20 degrees, we could say this is 200 degrees. That would be a bearing of 200 degrees, okay? Or you could say it is 20 degrees south of west, okay? Or you could say it's 70 degrees, I gotta write this in the right order. Yeah, it's south 70 degrees towards the west, okay? So you're going south and then you go 70 degrees towards the west. and that gives you the correct direction as well. So you could have written that in any of these three, okay? And that would describe this particular vector, okay? It has a magnitude of 180, right? And then it has a bearing of 200 degrees. So that would be the 180 miles, sorry, not degrees. And that would be the traditional way to write the vector. But you can also give the direction both of these forms. And so you need to recognize each form, okay? Okay, here's a problem. An airplane leaves an airport traveling at 450 miles per hour at an angle of 25 degrees east of south. Describe the location of the airplane 3 hours later. So basically, if I look at this problem, this is east and this is south. So 25 degrees east of south. So that'll be this right here. Good, 25 degrees east of the south. All right. Okay. And so yeah. So now we want to describe this particular vector that the airplane is traveling at. Okay? So let's do that. So number one, we want the magnitude of the vector. So the magnitude is rate times time. So 3 times 450, 3 hours times 450 miles per hour. So see the dimensional analysis, the hours cancel. And so we get 1,350 miles. That's the magnitude. And then the bearing, 25 degrees east of south, that's going to be 270 plus 25. So it'll have a bearing of 295 degrees. 25 plus 270. Okay? Now what we want to do at this point is we want to then convert this to component form. So convert to component form. To describe the location of the vector in terms of 2 points or how far it is from where it's. So we know how far it is in the bearing, and now we're going to describe it in terms of y and x values, okay? And so we want to figure those out. And the way we do that, if you remember, x is equal to the magnitude of the vector, right? Times cosine of the bearing, and y is equal to the magnitude of the vector times the sine of the bearing. So in this case, it would be 1350 times cosine 295 degrees, and this would be 1350 times the sine 295 degrees. All right, and I can calculate both of those fairly quickly on my calculator. You can calculate them on your own if you wish. So 1350 sine of 295 degrees. So notice I checked my mode. So this says negative 1223.5 miles. And the next one is 1350. Oops, sorry, I wrote that in the wrong spot based on the one I calculated. And then I'll erase this one. Sorry, I did the sine first. Now I'm doing the cosine, which is 570.5 miles. Okay? And so we can describe this vector as 570.5 negative 1223.5. And that makes sense. Here's the 570 and here's the negative 1223, right? That'll get you to the point. So this is definitely in the correct quadrant. And so this means we're going to be 575 miles east of where we started and 1,223 miles south of where we started. So both of those. Or you could think of it in terms of this one, we're 1,350 miles at a 295-degree bearing. All right? So that's what you want to do. You want to find the location based on both of those. All right? Okay? Any questions? I hope that feels like you got a pretty good understanding of what you need to do for vectors, direction, and magnitude. Alrighty? Talk to you later. Bye.